Okay, so we've got 4 days of class left, including today. Yay! So what we're going to do is that we are going to focus on chapter 25 on Amines. Okay, so that'll be the last material that we cover. It'll take us 2 or 3 days, and then we'll have at least 1 day probably to do some review, some kind of review or something like that before the final. All right, remember, the final's on Friday, so we do have the in-class final just like before. We'll be split into 2 different rooms, and I'll post room assignments before we get to that point. The computer final starts on Friday after the written part and goes through Tuesday at 10:30 p.m. That's when the testing center closes during finals week. For the final, you only get a single try at the computer portion of the exam. Right? So you're well trained now. You don't need that second try. We have our ongoing, if you're feeling at all behind, make sure to go to the SI sessions. Use the UTF office hours. They sit there by themselves most of the time. Just waiting for you guys to come and ask them questions. We've already set up, or Jake has already set up, the super session for the final. That's going to be next Tuesday from 4:30 to 6:30, and we will have another 2-hour review session as well that still needs to be scheduled. All right? Any questions? The final will likely be 26 computer questions up from 25. No. 26. Up from 25. That extra 1 question being because you have the final. It will be 30 questions up from 25. And there will probably be 6 written questions rather than just 4. Okay? The format will be the same. I would say, clearly there's a lot of material to cover. One place that you can start at least is to go back and go over the old exams. You can rework them. There are fresh copies on Canvas. There are copies of the multiple choice portion. You could redo those. There will be some new material, but what I promise not to do is to use the final to go back and pick out all the stuff I never tested you on before. Right? Doesn't mean that there won't be things that weren't explicitly on the old exams, but I won't just focus on something like that. All right? Any questions? All right, so let's do a clicker question before we go into the new chapter. Okay, so the question from the clicker was, when do we do the Robinson annulation? Right? And so in the Robinson annulation, what we need is the alpha beta unsaturated carbonyl, and we need, some kind of ketone or something like that. So it seems like, let's see here. We did some examples that were just, we could do something even like this, right? And what we did, if we were working backwards, is that we cut this one and something else. Let's put something here. And we cut this one. So something's not right. Yeah, that's a good question, and I'm kind of floundering here.
Yeah, because in the textbook it shows the conditions as being identical for both. So
yeah.
does the microreaction ever actually happen, or does it always just proceed to that Robinson annulation?
No, it doesn't always proceed to the Robinson annulation. Let me address that next time. I'll look at it and try to address that better. I'm too much thinking about amines right now. Yeah.
Wouldn't it just proceed if it could make a 5 or 6 member ring? Otherwise it wouldn't? Like for,
Because you're gonna have a 1,5 dicarbonyl compound.
but like in the clicker question, it could only form a 4 member ring, which has too much steric hindrance, so why would it go to that?
Right, so, well, if we move backwards from this, right, so this would go back, I don't know if this is even the best. This would be the OH here. This would be from the intramolecular aldol. So if we went back to that, we would be having something like this, right? And we would have made this bond right here from this alpha beta unsaturated carbonyl and this enolate, right? So that would be the aldol. So if in this, or this, yeah, this would be the Robinson annulation. So if this was, like we had on that last one, if this was like some kind of OR, that would be this right here. Would have, yeah, no, that's, well, let's not just kind of use time here. Let me try to see if I can address that better next time and be more succinct about it. All right, so today what we're going to do is we are going to talk about amines. We've seen amines a little bit before, but we'll go into more detail now. We're going to first talk about the structure and bonding. We'll learn how to name them. We haven't done that before. We'll talk about some physical properties including spectroscopy, so structure determination. We got to refresh our memories a little bit on that. And then after that, if we get further, we'll be looking at ways to make amines and then some reactions of amines. Okay? We are going to cover most of this chapter, except we're going to skip. I should have written down what the section number was, but we're going to skip what is called the Hoffman elimination. I think this is like this. Hoffman elimination. And I'm not going to cover, a bunch about. There's a lot of cool naturally occurring amines, right? So take a look at those if you want for extra stuff, but I'm not going to specifically cover those. All right? So this is what I said. We're going to start out with structure. Okay, so remember that amines are nitrogen-containing organic molecules, and they are related to the most simple kind of amine is a nitrogen with just 3 hydrogens on it. It's kind of hard to actually call that organic because there's no carbon there. But what's this molecule? This is ammonia, right? Right? You've probably all smelled ammonia before. It's in, Windex, glass cleaner, that kind of stuff. All right, so if we start with ammonia and we replace those hydrogens with alkyl groups, we make amines, and those amines can be classified based upon the number of alkyl groups that are attached to the nitrogen. So if we have 1 alkyl group attached to the nitrogen and 2 hydrogens, this is a primary amine. If we have 2 alkyl groups, it's secondary, and 3 alkyl groups is tertiary. Okay, this is the same kind of classification as we could use for amides, right? But it's different than what we used for, say, primary, secondary, and tertiary alkyl halides or alcohols, because in those cases we're looking at the carbon that's attached to the functional group and seeing how many alkyl groups are attached to that carbon. Okay? So it's a little bit different in that way. We do have one more version of an amine, and that is when the nitrogen actually has 4 bonds. Like this, it would have a plus charge, and those bonds could be to alkyl groups or to hydrogens, and this is an ammonium ion. All right, so nitrogen typically has 3 bonds and a non-bonding pair when it's neutral. If it has 4 bonds, it has a plus charge. Yeah?
So it's still considered an ammonium ion even if there are groups there and not just...
Right, so good question. So the question is, if those are R groups, is it still called an ammonium ion? So technically, ammonium is NH4+, but any quaternary amine salt like that is referred to as an ammonium ion. Okay, so it's kind of a generic term as well. Okay? So as far as geometries, the non-bonding pair has to take up some space. And so what would be the hybridization around the nitrogen in an amine? sp2, sp3, right? Because we have 4 pairs of electrons around the nitrogen, and they each need to go into an orbital. Okay, so normal amines like this are sp3 hybridized, so the nitrogen is actually hybridized tetrahedral, but one of those points of the tetrahedral is just a non-bonding pair. So what we would observe, so this is tetrahedral, what we would actually observe, though, is kind of a trigonal pyramid, right, of the atoms. So the atoms make up a trigonal pyramid. All right, so the angles, though, are, here it shows the carbon, nitrogen, carbon at 108, so they're close to the ideal tetrahedral angles of 109.5. Okay? If we look at an amine like this, one that has 3 different groups plus a non-bonding pair attached, we could think that this was a chiral molecule, right? Because it's essentially 4 different things around it. And it could be if it was stuck in this form, but in reality what happens is this kind of flips back and forth. It inverts. And so it's going to go through kind of an intermediate like this, or a transition state, I guess, where it's planar. This would be CH2, CH3, and H, where this is a p orbital in the middle. So this would be sp2 hybridized, and then it can flip over onto the other side. Like this. Okay? So essentially what would be the enantiomers are easily interconvertible. All right? So we don't usually think of amines as being chiral. Yes?
So enantiomers have to go through that intermediate, essentially.
Yes, they would have to go through that intermediate, but it flips at a reasonably low temperature. Okay? The only place, question first.
Yeah, with tertiary amine, so it's big bulky R groups that it couldn't do this quickly?
So good question. So if the R groups are too big, would it not do this? I think it would still do that because, in fact, as it goes through the transition state, the R groups actually get farther apart, right? And then they would come back together. So, and each enantiomer should have the same steric issues, okay? The places where it wouldn't happen is, for example, if the amine was into some kind of ring system where it just is held in that position, right, and it can't flip, or if we have 4 bonds, like an ammonium ion, then there's no non-bonding pair and it can't flip. So ammonium ions can be chiral, but amines are not considered to be chiral. Okay? Okay, so naming. Can somebody maybe close that door up there since they're chit-chatting out there so much? All right, so thank you.
Can you say that?
All right, so naming amines is pretty easy. We take the longest carbon chain that is attached to the nitrogen and we drop the E and we say alkane amine. Okay, so amine is the suffix that we use. All right, so if we start over here with the simplest one, right, this is ammonia. Right, these other ones we would just count the carbon chain, 1, 2, 3, and so this is a propane amine. But the amine could be either at the 1 position or the 2 position. So we have to specify where it's attached. And so the way we put this is propane 1 amine. All right. What would be the longest chain in the second compound that we would use as the parent name? How many? 6, right? So the longest chain is right here, right? We don't count across the nitrogen. And of course, we're going to give the nitrogen, the amine, the lowest number that we can. Okay, so we're going to start numbering on the right. 1, 2, 3, 4, 5, 6. So this is a hexane 3 amine. Hexane 3 amine. And then we have 2 different substituents, right? Where did that go? Dang that. The green color disappeared. All right, we have a methyl group here, and we have an ethyl group up here. All right, so how are we going to say that that ethyl group is attached to the nitrogen and not to the parent? We put an N in front, right? And does that N, do we alphabetize the N? No. Do we always put the N substituent first? No. Okay, we alphabetize the substituent, and the N is just like a number. Okay, we don't have to put those in order. So in this case, ethyl does come before methyl in the alphabet, so we are going to say N-ethyl and 5-methyl hexane 3 amine. Okay? If we had 2 ethyl groups on the nitrogen, would we just say N-diethyl? N-diethyl, right? We have to put an N, just like we'd put a number for each of those alkyl groups. If there's 2 of them, then it takes 2 N's. All right, so the last one up here is a really common amine in the lab, and it's usually referred to just by its common name. Yeah, question?
So why don't we put N for the parent group as well? Like on the last one, because I guess technically there are 2 substituents on the right?
Right, okay, so the question is why don't we put an N on the parent? because the parent is just an alkane chain, and we just use the 3 there to tell where the amine. We're already taking care of the nitrogen in the parent by saying amine at the end. Okay? So we usually use just a common name for this. And when we use common names, all we do is list the alkyl groups and then say amine. Right? So this is usually referred to as triethylamine. Okay? What would it be if we named it using the IUPAC naming?
And try.
No, we still have to have a parent, right?
Oh, so then it'd be like NN.
Right, NN diethylethanamine.
So you need,
Okay? Triethylamine's easier, right?
yeah.
Okay, so we can have diamines too. We're not going to worry about, here, let me change these. We're not going to worry about, well, they would be not that, well, we just say whatever it was, pentane 1,5-diamine or something like that. But these, there's 2 of these where it has N equals 2. So that means there would be 4 carbons in between. It would be a butane diamine. And just based upon the common name, it gives you a sense of one of the physical properties of these compounds. So N equals 2, its common name is called putrescine. All right, and if we add just one more carbon in there, N equals 3, so this is a pentane diamine. Its common name is called cadaverine. Okay, so you can imagine what these might smell like, right? Not very good. All right, so another type of amine are the amines that have the nitrogen attached to a benzene ring, right? So we would have a parent compound like this. What's that parent called? Is aniline. Okay. Right? And so in this case, we have 2 different substituents. What's this substituent here? Isopropyl, and an ethyl over here. So again, it just turns out that the N substituted group comes first, just because ethyl comes before isopropyl. Remember, we alphabetized the iso. So it would be N ethyl. Let's use numbers here. 1, 2, 3. 3 isopropyl aniline. All right? Okay.
You don't need to include the like ortho, meta, or para when talking about the 2 substituents.
Well, the reason I don't in that case, because I just use a numbering system instead. Remember, we could use either way. So I think I think it's going to be more complicated here to use, what would it be if it was the 1-3 arrangement? What do we call that? Meta, right? But then, yeah, I'm not sure how you would do this and still put the N-ethyl on that one. So I think the number here is more straightforward to use. This is, again, just after the book. I know it's kind of small, but I made it as big as I could. All right, so if we, yeah.
On the last slide when you're naming the
All right, so when we talk about boiling points and melting points, what we really have to consider is the intermolecular forces, right? Between the two, between different molecules of the same molecule, I guess. So we're looking at intermolecular forces. Right? And those forces include just van der Waals interactions, which is just the alkyl portions having transient dipoles. That's the weakest kind of interaction. We can have dipole-dipole interactions, which are next. And then we can have the hydrogen bonds, which are also dipole-dipole interactions, but kind of a stronger, important type. So if we compare, here's an ether versus an amine versus an alcohol, we notice that they picked 3 compounds that all have the same number of kind of heavy atoms, so carbon or nitrogen or oxygen. So they all have molecular weights that are about the same. And we see that the ether has really a very low boiling point. If you can't see it, it's 38 degrees Celsius. The amine is 78, and the alcohol is 118. Okay, so why would they be in that order? The alcohol has a hydrogen bond. That's true. What about the amine?
The primary amine also hydrogen bonds, but it's less electronegative
Mm-hmm.
than the oxygen, so it doesn't make as strong of a hydrogen bond.
It is true. So the issue here is that both amines and alcohols can hydrogen bond. So remember, hydrogen bonding, let's draw it for the amine here. If we have something like this, that wasn't very good. Remember, because the nitrogen is more electronegative than hydrogen, it has a delta minus on the nitrogen and a delta plus on the hydrogens. And so the delta plus hydrogens can orient themselves to the delta minus on the nitrogen. Okay? So alcohols can do the same thing. The hydrogen orients to the oxygen. But because oxygen is more electronegative, the oxygen-hydrogen bond is more polar than the nitrogen-hydrogen bond. So that allows it to make stronger hydrogen bonds. Okay? However, notice that the amine, the primary amine, has 2 hydrogens. And so it can actually make 2 hydrogen bonds. But even with 2 hydrogen bonds, so this can do 2 times H bonds. Even with 2 hydrogen bonds, it still has a lower boiling point than the alcohol with only a single hydrogen bond. Okay? If we compare that primary amine to, down here, a secondary amine that has the same number of carbons, notice that the boiling point goes from 78 down to 56. And that's because the secondary amine can only have a single hydrogen bond. It only has a single hydrogen to make a hydrogen bond. If we go to a tertiary amine, there's no hydrogen bond. And notice this is at 38. That's essentially the same as the ether. Okay? So, the boiling point and the melting point depend upon how many hydrogen bonds those can make. As far as solubility, we kind of follow the same rules as we did with alcohols and other kinds of groups like this. The amines, they're always soluble in organic solvents, but only if they have roughly 5 or less carbons on them will they be water soluble. Okay? Yeah, question?
Sorry, question back on the boiling point. When we talked about carboxylic acid derivatives
Mhm.
at an amine,
Mm-hmm.
that one had a higher boiling point than the carboxylic acid.
The amide?
The amide had a higher boiling point than the alcohol version of the carboxylic acid.
Mm-hmm.
So I'm curious why it's opposite in this case with the
Well, I think for the amides and the carboxylic acids, because they can they have resonance that has some charges, or the carboxylic acids can dimerize as well, right? And so they kind of behave like they're twice as big, almost. And I think the amides have a stronger delta plus, delta minus because they have this resonance as well, I think, if I remember back. Okay, so if we have few carbons, it's water soluble. No matter the carbons, it's always organic soluble. And remember that amines, like carboxylic acids, the ionization state can change as we change the pH. Okay, we went through this before. If we have just some amine like this, if we add acid, it forms the ammonium ion, and the ammonium ion is going to be soluble in water. Okay, so if that R group is more than 5 carbons, then the free amine on the left, or like if you've heard of the term free base, right, for cocaine or something like that, what that means, just heard of it, right? The free base is the neutral amine, like this. So it's the free base versus the ammonium ion. Okay, so if we add acid, we protonate the amine to form the ammonium ion. The ammonium ion becomes soluble in water. If we add then base, it deprotonates, it goes back to the free base, and that would be soluble in organic solvents. So it's just like the carboxylic acids. By changing the pH, we can change the solubility of the amine. All right, what about spectroscopy? Okay, so starting out with mass spectrometry. Here's a mass spectrum of just, what is this, 1, 2, 3, 4, butane 1-amine. Couple of things to notice is that, remember that there was something called the nitrogen rule. And that said that if we had an odd number of nitrogens, then the molecular ion should have an odd mass, right? And notice for this butane amine, we have a molecular ion at 73, okay? So if we have an odd number of nitrogens, then the molecular ion will have an odd mass. Yeah?
Is it a strong indicator that there's a nitrogen in the compound if the molecular ion is, the molecular peak is odd?
So the question is, if the molecular ion peak is odd, is that a strong indication of nitrogen? Absolutely. Okay, because if there's no nitrogen, then it cannot be odd. Okay, but it could be 1 nitrogen, it could be 3 nitrogens, it could be 5, it could be 7. You know, I'm probably not going to give you a structure that has 7 nitrogens in it, right? But having an odd, mass, if you're sure that's the molecular ion, then that means that there's at least 1 nitrogen. Yeah, question?
How do you know it's not like a phosphorus or a fluorine or a chlorine in the compound to make it have odd numbers?
Well, fluorine, so the question is, how do we know it's not other atoms in there as well? So fluorine would not cause it to be an odd mass, okay? And I think phosphorus is the same. It's a thing where we have it's partly because we have this odd valence. We have 3 bonds to make it neutral. And so nitrogen is kind of a unique atom in this sense. Okay? Let's see, what else? So if we go from 73 down to 30, we didn't really talk much about fragmentation, but groups like alcohols and amines, what they do is they cleave on the opposite side of what we could call the alpha position, right? The position that's directly attached to the functional group. And so this would cleave at that point, and it makes an ion that looks like this. And this is M over Z. What does M over Z mean? Mass to charge ratio equals 30. Okay, so any kind of, we have here butane 1-amine. We could have octane 1-amine. It would be a much higher molecular ion, but it would still cleave in the same way, and this ion at 30 would be the prominent ion. Okay, that just is characteristic of some linear primary amine. Okay? If we look at the IR spectroscopy, the most characteristic absorptions are the NH stretches. Okay, and they are usually in a region that's, similar to alcohol stretches. Okay, and so these are somewhere in the 3,300 to 3,500 reciprocal centimeters, and this is an NH. All right, if we have a primary amine and there's two NHs, then we see two peaks. All right, and I think it's because they're stretching. They can stretch in a symmetrical fashion, or they can stretch in an asymmetrical fashion. Okay, so we get two peaks. If we have a secondary amine like this, there's only one NH, and we see only a single peak. All right, so this one can sometimes be a little bit hard to distinguish from just an alcohol as well. All right, but it's not as prominent as what we usually see for an alcohol, but things don't always end up exactly like we hope. Yeah.
If we had an alcohol and an amine in the same structure, then that would probably be hidden by the alcohol.
If we have, so the question is, if we have an alcohol and an amine, what would it look like? And they might easily just blend together, and it would be hard to tell. All right. If we have a tertiary amine, of course, there's no NH now, and so there would be no NH stretch, no NH peak. Okay? So this allows us to kind of tell between primary, secondary, tertiary. Remember that amides show the same type of effect, but the NH peaks for amides are actually much stronger, but it's the same thing. If we have a primary amine, there's two amide, there's two NHs, we see two peaks. If it's secondary, we see one. Tertiary, none. Okay? Yeah, question.
Just a question. So the only real way to identify a tertiary amine is to also have mass spec to see that on number essentially.
Right, so the only other way to determine the presence of a tertiary amine would be the mass spec, if it was an odd mass. And then, we're not going to get much from the IR, really, right? And then NMR, but that's kind of more indirect as well, based upon chemical shift and things like that. So let's look at... Okay, so here, hopefully we can see them good enough. Here's two proton NMR spectra. These are both for isomers of a compound with, they're both isomers, and they have molecular formulas of C8H11N. So notice that for amines, the generic formula is CnH2n plus 3. Okay, because we've essentially added one more hydrogen. All right, so how many unsaturations would there be? You guys remember how to do that? The unsaturations, remember, equals the number of carbons. Yeah, question. Oh, huh? 4? Okay. Right. So let me just 8, the number of carbons, minus half the number of hydrogens, plus half the number of nitrogens, plus 1. Okay? So what's important is you don't just take the 11 halves and add a half and make 12 halves. What you really need to do is to subtract the 11 halves from the 8, because that's a negative 11 halves. So that is whatever, 11 halves, 5.5, right? So it gives you 2.5, plus a half is 3, plus 1 equals 4. We have some good arithmetic students here. Fractions even. All right, so let's look at these spectra then. Let's look at the top one. All right, so what do we see, if you can see it good enough? Right, so this region down here, what would that be for? So this is for the benzene region. Okay, so this is the aromatic. The fact that we see 5 protons in the aromatic means that we have a benzene that's mono-substituted, right? Out of a benzene, it only has 5 hydrogens. Oops. So we have one like this. What else do we have? Yeah, they're getting out so early over there. So unfair. All right, so what are these two go to? Here's the drawings. Here's a quartet and a triplet. It's an ethyl group, right? So the quartet is the CH2 group. It has a methyl group next to it, so 3 hydrogens, n plus 1 equals a quartet. So this is an ethyl group, CH2, CH3. Its chemical shift of the CH2 group is just over 3, so that means it's probably attached to the nitrogen, right? And then we have one more peak left over right here, which is just a little broad peak, and that's an NH. And up here, I said we had an IR absorption at one peak at 3,400, so that's the NH. So this is going to be an N with an H on it and an ethyl group attached. Okay? So in the last minute and a half, let's look at the bottom one. Okay, here's the IR. If you can't see it, it says there's peaks at 3,430 and 3,350. The aromatic region shows us 2 peaks. They both look like doublets, and each worth 2. So what does that tell us about the benzene ring?
Substitute.
Dye substituted. What about the actual arrangement? It's what? Para-substituted. Exactly right. Because this has the symmetry, right? And so these 2 peaks are going to be equivalent. And these other 2 peaks will be equivalent as well. And they're each doublets because they couple to the one next to them. Okay, so what are going to be the 2 groups attached to this para-substituted benzene ring? We have an NH2 because we have 2 amine protons and we have 2 stretches. Okay, we're almost done here. We got 5 seconds. And it's an ethyl group right there. Right? We did it. Perfect. No wasted time. Okay, I will see you guys tomorrow.